Wait. God damn it. I always forget. A little piece of paper. Alrighty. Hope everyone is doing alright today. Nice. Chill Saturday. So, doing a little random Saturday stream. Figured, not really sure what exactly my next, bot-related automation program will be right now. If I'm going to spend more time doing like bot building and stuff like that, I want to make sure that it's stuff that would be actually useful for other people. And so I'm not really sure, since I don't run my own massive Discord server. I'm not a regular streamer or anything. I'm not really sure exactly what tools would be useful for people in those situations. So I've kind of sent out some feelers to other people to try to see if there's any actual interest in those kind of tools, because if there are, hopefully I can do this a little more regularly, start building up a system and everything, and then, as the TikTok financial advisors say, build up that passive income stream. So I figured in the meantime, there is this really good neural network tutorial that I've been meaning to go through for a while now, and have just been putting it off, and figured, now is as good of a time as any to get that going. So there is this YouTube channel, SentDex, that I would highly recommend to anyone who wants to get into kind of the intro learning Python and learning some of the more advanced topics in Python. He has a lot of really good video series. He's where I went to when I first started learning how to program, especially in Python. But a while back, he made this book, it's a fucking beast, called Neural Networks from Scratch in Python. And the whole idea behind the book was to really start out from bare bones basics. A lot of your intro to AI and neural networks in Python pretty much just start with import TensorFlow, here's some data, and then the pre-installed library just does everything for you. And so the goal with this book was to start with effectively just vanilla Python and build a neural network starting, with that. And so the goal, by doing that, the hope is that you get a deep, rich understanding of why neural nets do what they do and how they're set up. And so by actually, going through everything step by step and doing it all on your own, you can grow for a better understanding of, okay, why would I use this activation function versus another activation function? Why is it that I would want my data or my neural network to have this many layers as opposed to that many layers? Or why would I want to use this layer structure compared to some other layer structure? And so doing that all from bare bones basics will hopefully give the user a better understanding of how that works. So to anyone watching, highly, highly, highly recommend this chat. I have to sign in to chat. Why do I have to sign in to chat? God damn it, Streamlabs. Just let me. Boom. So anyone watching at home, highly recommend you go check out his videos and buy the book while you're at it. So the plan right now is to kind of start going through the book. I think the best way to do this, let's avoid accidentally, there we go. So unfortunately, I have a legally obtained ebook version here. But the problem is that when I download the ebook version, it attaches my name at the bottom, which you can't see right now. But if I were to scroll down to another page, it would have chapter 2, blah, 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 and then it would have my email address, my normal, real email address on there, which has kind of some identifying information, which I'd rather not put on stream. So unfortunately, not the best content, but I think the best way to go about doing it right now is just have the book kind of off to the side. And then I can pretty much just stream my actual IDE while I have the book kind of over here on my other monitor that you are not allowed to see, and then just go through it that way. And then I can kind of explain what it is I'm doing and why I'm doing what I'm setting up. So it will be some very, very dull streaming, but hopefully my award-winning personality will draw people in. All right, so go in here, set up Conda. What is the command to actually just create neural networks from scratch? Target prefix is the base prefix of boarding. Okay, Conda create a new environment from a list of specified packages. Okay, so let's do Conda create -h. Figure out what it is we're doing wrong. H, clone environment path, channel, use local overrides. I just want to give it a name. I don't want it to specify packages to install or update in the Conda environment. -n environment name. Okay, so if I do Conda -name, proceed, yes. Okay, so then Conda activate, and then, all right, sweet. Now we're in the NS, the neural net environment, and then we're gonna wanna do a pip install. We're probably gonna want NumPy, already satisfied, and pip install matplotlib. Probably also already satisfied, cool. Just to make sure those are all installed. So over here, I'm skipping through a lot of the book because a while back I started going over this. And a lot of it is pretty fundamental. So the general idea is that we're going to have some set of inputs, be it which we'll put as a list or a vector, 1, 2, 3. I have some weights, 4, 5, 6, and then using some combination of inputs and weights, that'll help us get we'll combine these in some fashion that will give us our desired output. So like the simplest way that we might do this is just to go through and do like input 0 times, nope, where's the multiply, weights 0 plus, to go through, boop, boop, change all of these. So this would be like a really rudimentary way to set up print answer. Oh yeah, and yeah, I might want to save this. For the time being, let's just call this main. And over here, I think I'm actually going to want a terminal in. We're just going to throw a console in here for the time being. And then if I actually run this, execute console, blah, blah, blah. Yeah, let's just run. Cool. So here, yeah, we did 1 times 4, 4, 2 times 5, 10, 3 times 6 is 18. So 18 plus 10 is 28, plus 4 is 32. Nice. Everything works as intended. And then maybe as we start going on, we'll want to do like a bias, because maybe for whatever reason we just want what is effectively like a DC output. And so for right now, we'll just set that to be 10. And then no matter what this is, we're just going to want to add 10 to every outcome. So now we get a nice 42 out of all of these. Boom. So that is kind of the most bare bones neural net setup. We have some inputs, some weights, and then in theory, what we're going to eventually start doing is that we're going to want to start shifting these weights and biases to be optimized in some way that it gives us a desired output. So it might be that our desired output here is not 42, but maybe we want 50. That's what we want. And so the way that we're going to eventually start telling the computer to do this is just guess and check different values for these guys to see which combination of weights and biases and give us an output of 50. Altogether code, input and weights to produce. Yep. And yeah, the other thing is that like there's no real reason this has to be limited to 3. Like in theory, this could be, you know, any number of inputs and weights. And so this could eventually, and the reason why we're going to effectively need to automate this process is that we could have something like inputs, you know, 1023. And so this is going to be like way too hard for me to go through and write out all one by one because I'm lazy and I don't want to do that. So eventually we're going to need to set up a system that can automatically adjust to any number of inputs and weights. And at that point, that is when we start falling into the hell that is linear algebra. Neural networks typically have layers that consist of more than one neuron. Layers are nothing more than a group of neurons. Let's say we have a scenario with 3. 2 additional makeup sets, 2 additional biases. Inputs, weights, biases, output is all of that jazz. So yeah, so eventually, as kind of a slightly more here's the real test. Can I just copy and paste this straight from, I can. God, it is good, everyone. So I should be able to just copy, now will let me do multiple lines. It will. The future is a magical thing. So now we might have some system where we have more inputs and we have a bunch of different sets of weights. And then we're also going to have a bunch of different biases that we want. And so we can kind of string together what we're going to call our neurons here. And we're just going to print outputs. And so now this should be a vector of outputs where we have kind of our first neuron here where we're taking all the inputs and all the different weights, and that'll give us this first little output. And then we're going to take all the inputs with the second set of weights, and that'll give us this second output, and then so on and so forth. And then we get this third output with different biases for all of these. And then what I know that this is going to lead to is that this is then going to become our, input 2 is going to equal this over here. And then we'll have another set of weights and biases, and then we'll do it all again, and we'll have output 2. And then we can kind of start stringing these processes all together as many times as our heart desires to get kind of more complicated and complicated models. What? Nice. Got all these nice little animations, which I will not be showing you because I'm not really exactly sure where the, oh no, I lost my download. I don't want that. There we go. There we go. Nice. Layer has connections to every neuron in the previous layer. This is a very common type of neural network. But it should be noted that there is no requirement to fully connect everything like it is. At this point, we've only shown code for a single layer with very few neurons. Imagine coding many more layers and more neurons. This would get very challenging to code. Okay. So now, for bad content, but my own edification. So pretty much what we're going to want to do set up, say, some inputs layer. We're going to do 1, 2, 3, and 2.5. And then we'll have weights, which we will set up to be a list of lists. So this way we don't have to have like weights 1, weights 2, blah, blah, blah. Weight, comma, negative 0.51. So that's effectively our weights 1. And then weights 2, negative 0.9, 0.3, negative 0.5, weights 2, and then weights 3, so 0.87. Boom. Then we can have bias C, bias says 2, 3, 4. And then now we're going to set up a layer outputs just to be an empty list for now, maybe if I can hit the right keys. And for neuron weights and neuron bias and zip, we're going to want to zip these together. And do neuron output. Start off with that being 0, and input weight in zip inputs, comma, neuron weights. So for each of these we want neuron output to equal the n input multiplied by the weight. Boom. So we got neuron. Okay, turned off the fan because I guess that was coming through a little bit. Still had the fan going, but a little less, a little slower. So hopefully that cranking noise isn't coming through. Add a bias, neuron output, bias, and we'll go out a layer. Neuron. So I want my output to be whatever that old value was, but then I also want to tack on whatever bias I have. Add that as just kind of a DC offset. It's yelling at me. Undefined name weights, because I before E, except after C. Boom. And then this list here is just going to be our, we're just going to append our output. Wait, no. On there. And then once we go through all of that, let's just print it out for posterity. So we run this, nice. And we get our nice little output here. So this is effectively going through what we had earlier, where before we were kind of explicitly typing out, okay, input 0, input 1, into blah, 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 until we got all through. But now wrapping that up in some for loops, just so that we can automatically spit that out. Dynamic and scalable way. Confused print. Ooh, now it's starting out tensors. What are tensors? Tensors are things that transform like tensors. Subtle differences. So yeah, now it's just going through the idea of a list, and then you have a list of lists, and then you can kind of keep nesting your list as many times as we want, because it's not homologous. A list of lists is homologous if each list along the dimension is identically long. True for each dimension. To row, yada yada. A lot of basic linear algebra. Mm-hmm. Yeah. Okay. Skipping over all the linear algebra stuff. Dot product and vector addition. Yay. Okay, so this right now is just saying, okay, we can set up a dot product. Here's how a dot product works. Take the elements of each vector, add them together, multiply them, then add the products all up, and you get a dot product. And then we start getting into the advantages that we can have with NumPy. So when we do import NumPy as NP, then we can start representing a lot of these things as NumPy arrays rather than just lists. That'll give us a little bit more of mathematical rigor. So if we have our inputs here and our weights, that will do, actually I already had, get rid of that. So if I have my inputs and my weights and my bias, then I can just do numpy dot and then do inputs, weights, and then plus my bias. And we'll do output. Can't do an arrow because there's no line there, and then print output. So now I run this. Holy shit, look at that. All that code wrapped up in this one little function call. How cool is that? Yada yada. Breaking down what exactly that is. A layer of neurons with NumPy. Calculate the output layer of 3 neurons. Need to do a dot product. Some weights and biases produced. Yeah. Now it's just going through that NumPy is smart and just automatically knows effectively how to do vector math. And so now if we bump this up like so, format this properly. Boom. So now we have the same thing that we had before, where we have our 3 different sets of weights. We will also turn our biases into a list. We can now still do a list and some addition, and already the output should, nope, 4 and 4 by 3 not aligned because my dimensions are all off. Why are my... This is a... I really wish I had a way to just like draw on screen, because this is a 4x1 and I want to dot that with a 4x3. It won't work, so I think this needs to just be weights, inputs, and then output is not defined. And then this should get me, yeah. Cool. So yeah, just flipping that around, we got to remember our matrix math. These two guys here in the middle need to be happy with each other, and our output is going to be that. So 4 by 3. No, that's still wrong. Meh. So why is this working? Because this is what we're multiplying here, and we're ending up with one of these guys. So this should be a 4 by 3, 4 columns, 3 rows. We got 1, 2, blah, da, 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 ja. Okay, that's what we're doing. Yeah, we're doing, okay, got it. We're doing a 4 by 3 here, dotted with a 1 by 4. These boys on the outside match up, so we are green check mark. Good. These ones on the inside here match up, so we are green check mark. Or they don't match, but that just tells us what our output is going to be. So this is telling us we're going to have a 3, 1, 2, 3, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So this is going to be answer 1 is equal to, yeah, it's like A1. It's going to be A11, B1, A12, B2. So it's like A11, B1 plus A12, B2 plus dot, dot, dot. Yeah, I still remember how to do linear algebra. Cool. It's been a while since I've had to do any of this shit by hand, but by God, I'm gonna get there. Cool. So now we got our output. And we're effectively masters of machine learning now. All right, what are you doing? Yeah, input output biases. You do a dot product there. Equals. Okay, so right now in the book it's just going through and showing more explicitly what's. No, what is. Okay, what are you doing? First, we operated on neurons and inputs, and then we're adding the base to the next operation. We add 2 vectors using NumPy. Each ith element is added together, resulting in a new vector of the same size. This is both a simplification and an optimization, giving us simpler and faster code. This code and visuals for the dot product applied to the layer of neurons. So we have outputs, weights and inputs equal weights 0, so that, okay, it's going through and just breaking down the fact that the dot product already works in, oh, does it? Boo, boo, boo. Code and visuals for the dot product applied to a layer of neurons is equal to that list, which is definitely not that. What is this? I have no idea what it's trying to show. How to do it the wrong way? Sum of the dot product and biases with layer of neurons. Or this just without, oh, okay, no, this is showing without the biases. Okay, cool, okay. That makes more sense. Involving the dot product, the weights and inputs followed by vector addition of the biases, yada yada, input templates those biases, so explain the order parameters, dot, put shape, keys for passing us a batch of data. To train neural networks tend to receive data in batches. So far, this example of input data has been the only one sample or observation. Meaningful. Observation or a sample. Often neural networks expect to make many samples. It's faster training batches and parallel processing. Matrix products. Yay, multiplying matrices. Cool. Transposition of a matrix. Wow. Okay. Oh, hey, when we transpose, we do like a little rotation thingy. So the rows become columns, and the columns become rows. Cool. Skipping over a lot of this because it's like intro to linear algebra, which, you know, if you were coming at this, yeah, probably more from just a bare bones programming end, this would probably be pretty necessary. But given that most of this is just like, here's how dot products work, kind of just skimming over this. You can set up NumPy arrays. Turning a vector into a row vector. Expandems adds a new dimension to the index of the axis. The column vector matrix where the second dimension size equals 1. It's an array of shape n, 1. The NumPy can be created the same way as a row vector, but needs to be additionally transposed. Transposition turns rows into columns and columns into rows. To turn vector B into a row vector B, we'll use the same method that we used to turn vector A into row vector A. Then we can perform the transposition to make it. Okay. So yeah, just, okay, so NumPy arrays, you can just throw a dot t in. Yeah, right now all it's doing, it's saying that, like, hey, if we have A equals, 1, 2, 3, B equals 4, 5, 6, then we can do A equals NumPy array A. I'm not really sure why. Is that necessary? I'm gonna just try some shit real quick. NP dot A comma B So that just went through to 34, I guess, to make sure. Yeah. Now the book here has a bunch of extra brackets and transposes going on, which are definitely not necessary. Like NumPy is smart enough to just know what we want here and just do it automatically. Though I guess, yeah, if we were to do this all by hand, we would want this to be the transpose of B so that the dimensions matched up. But NumPy is smart enough just to kind of know what we're after and make it work. I guess what would happen then if we were to just wrap this up in an extra set of brackets? Would it automatically do the transpose then? Okay, so if we threw this in another set of brackets, then it's not going to automatically do the transpose for us. So then we would have to do a transpose of array B so that it wouldn't be a 1-3, it would be a 3-1. Then we run it and we're good. Okay, interesting. Two vectors, we took one in, transform into row vector, second one, transpose, run column vector, perform a matrix product that returned a matrix containing a single value. Okay, so it seems, just throwing in the extra bracket set makes it like, hey, no, this is a matrix, not just a one-dimensional list. All right, layer of neurons and batch of data with NumPy. Just learn this the operation matrix performs. We just need to perform transposition. That's a second argument. So we have a 3x4 multiplied by a 3x4 input weights. This respective input output weights. We need to perform the dot product in each input and each weight set. Wait, what? We mentioned that the second argument for NP dot is going to be our transposed weight. Oh, okay, yeah. Yay, linear algebra is fun. At least, if you were doing linear algebra and not watching someone on the screen go through linear algebra. Cool. So yeah, almost chapter 2 is really just, hey, this is like crash course in linear algebra in like 15 pages. Adding layers. Layer, 2 or more hidden layers.